All right, so you first want to go ahead and read through the problem, pause it as needed. And so there's two things to really make sure we understand the definition of. First is bipartite graph. So a bipartite graph is going to have one set of vertices over here, one set of vertices here. It doesn't really matter where they're positioned as long as there's two sets of vertices. This is a bipartite graph, but the thing that makes it a bipartite graph is that any vertex in the first set can only connect with vertices in the second set. They cannot, for example, connect to a vertex within itself. So that would not be allowed. That's a bipartite graph. And then a complete bipartite graph, you're just getting every possible connection that's allowed. So here, in this case, we would have 15 of them because each one of our five would connect with each one of the three over here. So this is a complete bipartite graph. And this particular one would be K5, 3 because there's five vertices in the first set, three in the second. So we're looking at specifically 10, 8. So I'm going to bring this on down, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. And then, of course, you would have all the connections there. So instead of K5, 3, we now have K10, 8. And this would give us 80 possible edges, right? Just because each of these 10 would connect with each of these 8. So that's a complete graph 10, 8. Now it's asking for 4 coloring. So we have 4 different colors, which means if we, for example, color this red, that means that none of the vertices in the other set could be red. This one cannot be red, this one cannot be red all the way down there. Now these over here, any of them, that's fine if they're red. And if we would color a second one blue here, that also means that nothing over here can be blue because this one's connected to all 8 vertices over there. And so we're putting in exactly, this means no yellows. And in order for this to work, we'd have to have a fourth color, which green would work here. But if we had it set up like this, and it's a complete graph, all of these 8 would have to be green if we're going to do it with 4 colors, because no reds are allowed, no blues are allowed, no yellows are allowed left side. So what happens then is we get into really just 3 cases. Case 1, so 3 colors for 10 vertices. So this is the set of 10. This is the setup that we have on the left. And then 1 color for the 8. Right, and remember, we can't use any of these 3 colors for the 8 because each of these 8 vertices is connected to all 10 of the ones on the left. And then case 2 would be 2 colors for the 10 and 2 colors for the 8. And of course, those would have to be the other 2 colors. You couldn't have any overlapping. And you might wonder, well, couldn't you just do 2 colors for the 10 and 1 color? That wouldn't break any rules with the colors, but we're saying proper 4 colorings. That means we have to use 4 colors. So it would not be allowed to use 2 colors for the 10 and just 1 for the 8. We have to use all 4. And then, of course, there's going to be a case 3 that I'll let you figure out what that would be. So let's just look at a specific case. Let's look at case 1 together. We want to figure out how many different ways to choose the colors. First of all, well, we have 4 options. So this is choose 3 colors. We have four possibilities. We're going to choose 3 of them. We're going to say which 3 are going to go with the 10 in that case. And then you have this one color, but you only have one color remaining. One choose one is just one. You don't really have to. Um, this is for the 10, and this is for the 8. But that's not enough. Just because we know we're going to use red, yellow, and blue, there's a lot of different ways to color red, yellow, and blue over here. So we need to multiply this by something else. Something needs to go in here. And what is that number? Well, if you think about it, these are distinct vertices. You can number them if you want, 5 all the way down to 10. They're distinct vertices, and they're going to be put into these color buckets. So we have distinguishable vertices into 3, this is 10, 3 distinguishable color buckets. And are we allowing empty? If we would allow empty, if you think about it, if we have a red bucket, a blue bucket, and a yellow bucket, and we allow empties, that means we wouldn't use all 3 colors, which means it wouldn't be in case 1. This has to have exactly 3 colors, not less. Otherwise, we're not going to get that proper 4 coloring, which means we're not allowing empties. Now you might ask yourself, how did I know that the colors were the the boxes and the vertices were the items? Because it might make more sense to have the vertices as the boxes and the colors as the item. Well, remember, we always have to make sure, first of all, that n is greater than or equal to k. The number of boxes is always, sorry, the number of items is always less than or equal to the number of boxes. But you could also think of it in terms of if we have these as the boxes and these as the items, we have a system going on like this. So vertices 1 and 2 get colored red, 3 is blue, and each of these 10 are going to get put in a bucket. That would give us a specific coloring here. What would happen if, on the other hand, we had, bucket 1, 2, 3, 4, all the way up to, if we had the boxes be the vertices, and then the 3 things were our items, well, that would just give us the 3 items here, and we could end up getting something like this, where red and yellow are items that both get put into box 1. Or we really just have 3 items that we're distributing into the boxes. That's going to leave at least 7, maybe more, of our vertices uncolored. So yeah, it may not be obvious just from the way the problem is posed what the items and what the boxes could be here, but try it both ways. If you let the vertices be your boxes and the colors be your item, it's just not going to work out. It's not going to give you the type of thing you need. Whereas if you have the colors be your boxes and each of these vertices is an item, well, that tells you exactly which vertices get with each color. It also guarantees that every vertex has one and only one color assigned to it, whereas this method here would not. So you're going to use the box and items chart to figure out what that number is that you multiply by this. And then this will be a complete set of solutions for case 1, because all of these solutions will have exactly 3 colors here on the 10 vertices, 1 color on the 8, and we don't have to make any other, all 8 just get colored that. There's no other choices. And then here, how we're going to distribute up the coloring for the 8. Now here you're going to have to be a little more careful because you're going to have to do 2 different colorings. You'll have 2 colors for the left, 2 colors for the right, and then you'll need to figure out all the different ways you could do those 2 colorings. But it's going to follow a similar pattern. And then don't forget case 3, of course.